Hello there, Mr. Sutton here, bringing you the BC Calculus 7-7 Extra Practice Number 3 solutions on geometric, nth term, and ratio tests. For this problem, we want to know a little bit about the summation from 1 to infinity of e to the n over pi to the n. For example, what is its value, or does it even converge at all? There's an option here for it diverging. So first thing to do, which is going to make this a little bit easier to look at, since these are both being raised to the nth power, I can rewrite this as e over pi, all of that raised to the n. And then we very quickly see that this is a geometric series with an r value, absolute value of r value at that, of e over pi. Now, since e is smaller than pi, that means that overall this number is less than 1. Which means by the geometric series test that this is going to converge. So then choice D, not an option. It's going to converge to something. It's just a matter of what is the sum. So to find the sum, we'll just use the infinite sum formula, S equals A1 over 1 minus R. For our A1 value, our first term of the series, that's what we get when we plug 1 in for n, and that is just going to be E over pi. The R value, well, we already established what it is here. Both the actual R value and the absolute value are E over pi. It's the actual R value that we're interested in here, though. So it is going to be 1 minus positive E over pi down there. And now just to simplify this so I can match it with one of the answer choices, let's simplify the denominator first by combining that into one big fraction down there. So this is really pi over pi minus E over pi. So I can write this as pi minus E over pi in the denominator. And then we see here that the pi's in these denominators are going to cancel, or you can multiply by the reciprocal. This is e over pi times pi over pi minus e. Either way, these two pi's here cancel. So we just end up with e over pi minus e, which is going to end up being answer choice B. On this one, we want to know if c is a positive real number, and the kth term of some series is k times ln of that positive c value. For what value of c, if any, does this infinite series converge? All right, so the way that this is set up, if we have k continually increasing times some constant, then for any c value such that ln of c does not equal 0, so basically as long as this thing you're multiplying k by is not 0, then the limit of k ln of c as you approach infinity is either going to be infinity or negative infinity. I mean, if we have something bigger, if c is a number that's larger than 1, then ln of that is going to come out to some positive constant, and k times that, if you keep increasing the value of k and adding those up, that's going to infinity. If c is a number less than 1, then the ln of that is going to give you some negative number, but k times that a bunch of times is going to make you go to negative infinity if you keep adding those together. So this is going to diverge then by the nth term test unless you have one specific c value. If your c value here is 1, so that ln of 1 is 0, and you're basically multiplying k by 0 and just adding a bunch of zeros over and over again, if c is 1, then this will converge, and that's it. So that would be choice A. For this problem, we want to know which of these statements has to be true about this infinite series with positive terms. If the limit as n approaches infinity of, this is the n plus 1th term over the a term, so that basically the n plus 1th ratio equals L. So this is all about the ratio test and understanding that. By the ratio test, you're going to converge if your nth ratio is a number that's less than 1. And if L is greater than 1, then your series would diverge. And if it's exactly 1, then we're inconclusive. So let's look at our answer choices and see if any of them match these criteria. So choice A, series converges if L equals 1/2. Well, 1/2 is less than 1, so A is a true statement. But let's just look at the others to see if we can eliminate them. Choice B, series converges if L equals 1. Well, we said 1 is an indecisive thing for the ratio test, so can't choose B. C, series converges if L equals 2. No, it would diverge if L is greater than 1. And same thing with D. It's going to diverge if L is infinity. That's a lot bigger than 1. So then choice A for sure. For this problem, we're asking which of these three statements is true. So let's go back and read the preconditions here. So they're telling us that we have an infinite series with nth term a that diverges. Then we have some partial sum, that's the sum from 0 to n of a. And then we have limit as n approaches infinity of b does not equal 0. So going through now these different options here. First one, limit as n approaches infinity of a sub n does not equal 0. So they're basing on this on the fact that this a series diverges. However, the fact that this series diverges does not imply necessarily that the nth term is 0. There are lots of diverging series that do not fail the nth term test. So this one is not necessarily true. Certainly, if this statement here were true, then we could conclude that the A series diverged, but it doesn't work the other way necessarily. Next statement, the limit as n approaches infinity of s sub n does not exist. Well, this s sub n as n approaches infinity is basically the infinite series that they said diverged up here. It's the same series. So because this series does diverge, that means this limit does not exist. So then the limit of the series itself does not exist, does not converge to a specific value. So this is a true statement. And then finally, this last one, they're saying the series with b as the nth term diverges. Well, they set up here that the limit of b, the nth term there, was not 0. So that means that this series then would fail to converge by the nth term test. So that would also be a true statement, that it diverges. So then options 2 and 3 were correct, so choice C. For this one, we're given the nth term of some series as the nth root of 2, which is kind of interesting. And we want to know which of the following statements about this series has to be true. So there's a few of these that we can eliminate right away. This one, for example, choice C, the series converges and the limit of the nth term does not equal 0. Well, this automatically fails the nth term test, so we know C is not the answer. D could be the answer, and choices A and B also could be answers. So we have to dig a little deeper here. But this is all about the nth term test, so let's actually take the limit of the nth term. I'm going to rewrite this as 2 to the, this would be 1 over n if it's the nth root. So as n approaches infinity, this exponent here, 1 over n, this fraction, is going to be approaching, well, it's bottom heavy, so this is going to be approaching 0. So then this whole thing is approaching 2 to the 0. And 2 to the 0, as we know, is 1. And 1, as we also know, is not 0. So therefore, there's only one answer choice left saying that the limit is not 0, and that was choice D. And that makes sense because if your limit of your nth term is not 0, then your series is going to fail the nth term test. So this series then diverges by the nth term test. So yeah, we got to pick choice D. For this problem, we want to know which series can be shown to converge by the ratio test. So you essentially need to take the limit as n approaches infinity of the n plus 1th term over the nth term and see which one of these comes out to a value that's less than 1. So if we get something bigger than 1, we would know the series diverged. If we got something exactly 1, the ratio test would be inconclusive. So with those ground rules, let's give it a shot. So we have n plus 1th term here. That's radical n plus 1 over n plus 1 plus 10 divided by the original. And as n approaches infinity, I mean, you could same change flip this thing, but you can see right away that you're essentially going to have radical n over n up top and radical n over n downstairs. And this whole thing is just going to come out to 1, which we know is inconclusive. So that's not the answer. Let's take a look at this one. So we have n plus 1 to the 10th over 10 to the n plus 1. All that over n to the 10th over 10 to the n. If you wanted to, you could get rid of this 1 in here to call this n to the 10th. You really can't get rid of the 1 in the exponent, though. It doesn't quite work that way with ignoring slower growing terms if the term is in an exponent. So at any rate, I'm just going to same change flip all this. So I've got n plus 1 to the 10th times 10 to the n over 10 to the n plus 1 times n to the 10th. So we can reduce this to 1 over 10 for those exponential terms. And these terms here, these are both dominant terms with a dominant term of n to the 10th, so those are just going to end up canceling out. So we end up with 1/10, which is less than 1. So definitely ratio test shows that this converges. But let's just take a look at the other ones to see if we can really eliminate them. So this one, we have our n plus 1th term over the nth term. And I can turn this into just ln of n over n squared, which all comes out to 1. So inconclusive for that one. And then down here, we have n plus 1 over n plus 1 to the 4th over just n plus 1 over n to the 4th. This is going to be n over n to the 4th. And down here we also have n over n to the 4th. All comes out to 1. Inconclusive. So definitely then choice B. For this one, we want to know which of these series converges. So basically 3 problems for the price of 1 here. That was nice of them. Let's take a look at this first one. So this one isn't quite geometric because we have this n out in front. Without that, this would be a geometric series. So instead, let's go ahead and since it looks like this thing is going to pass the nth term test, you have basically e to the n growing faster than just n. Let's go ahead and use the ratio test to sort this out. So I have limit as n approaches infinity of absolute value of, and now I just need the n plus 1th term. So I'm going to write that as n plus 1 because we have an n in the numerator over e to the n plus 1 because we essentially have an e to the n in the denominator. All that over n over e to the n. Same change, flip that stuff around. We've got e to the n times n plus 1 upstairs. And downstairs we have e to the n plus 1 times n. E to the n's I can cancel out a little bit there, leaving just an e downstairs. And these n's are also going to eventually cancel. This 1 basically gets ignored as n goes to infinity. So n over n is just going to cancel. So we end up with a ratio, an nth term ratio of 1 over e. Since e is greater than 1, this whole fraction is going to be less than 1, which means that this converges by the ratio test. So any answer choice that does not have option 1 in it, such as B, has to be eliminated. Now let's take a look at option number 2. So for this one, this is one where it helps to know which functions grow faster than others. If you take the limit as n approaches infinity on this one, you'll see that n factorial is a much faster growing function than really any exponential function. So this goes to infinity. Since that's not 0, this series diverges by the nth term test. So anything that has 2 in it can be eliminated, so choice C is out. So it's really down to either choices A or D. If 3 works, we pick D. If not, we pick A. So let's look at 3. Now this one is just a mess. We've got multiple factorials going on here. So as a general rule, whenever I see a problem with more than 1 factorial in it, I'm definitely going to try the ratio test on that. I've really got no idea which one of these is growing faster for the nth term test. So let's just go to ratio test. I mean, anything that would have failed by the nth term test, the ratio test will also catch. It just takes a little longer. So I've got the limit of the n plus 1th term over the nth term. Now I'm actually going to split up this factorial into n factorial times n factorial. So for my n plus 1th term, I'm going to end up with n plus 1 factorial times n plus 1 factorial. Down here, since you've really got 2 parentheses n plus 1, this is going to be 2n plus 2 factorial for that n plus 1th term. So be careful getting your n plus 1th term out of that. And then downstairs I'll have n factorial over 2n factorial. So now same change flip. I've got these double n plus 1 factorials times the 2n factorial. And I have the 2n plus 2 factorial times nn, or n factorial. Time to cancel some things out. So each of these n plus 1 factorials can cancel a bit with the n factorial. This is basically n plus 1 times n factorial. So when you cancel this with an n factorial, you're just left with an n plus 1. And we've got 2 of those. Now the 2n factorial interacts with the 2n plus 2 factorial. 2n plus 2 factorial is essentially 2n plus 2 times 2n plus 1 times, well, 2n factorial. So when the 2n factorial and the 2n, or when the 2n plus 2 factorial, I should say, and the 2n factorial interact, they cancel, leaving only a 2n plus 2 and a 2n plus 1 downstairs, because the other 2n factorial got canceled out with this 2n factorial. Okay, so a whole lot of factorials going on, but they're gone now. All that's left is essentially two polynomials. So upstairs, our dominant term is going to be an n squared if we multiply all this out. Downstairs, we've got a 4n squared. So those end up just reducing to 1/4. Since that is a number that is less than 1, we can finally conclude that this series will converge by the ratio test. So then options 1 and 3 converged, giving us choice D. For those of you who really like the nth term test, this problem's for you. On this one, the nth term test can be used to determine divergence for each of the following except. So we're going to run the nth term test on all of these, and then whichever one is inconclusive, we're going to pick that as the answer. So for this first one, limit as n approaches infinity of arctan of n. Well, remember, arctan is taking the slope of an angle and giving you back the angle. So as your slope becomes infinite on the unit circle, you're essentially approaching the angle at the top of the unit circle, which is pi over 2. Pi over 2 is not 0, so we can show that this series diverges by the nth term test. On to the next then, limit of this one as n approaches infinity. Well, since we have 1 over something that's growing, this is going to go to 0. And this does not prove that it converges. It certainly doesn't prove it diverges. This is inconclusive. So this is probably the answer, but let's keep going just to be sure. On this one now, taking my limit, if I multiply everything out, I basically have a dominant term of n squared in the numerator, also a dominant term of n squared in the denominator. So that means that we have basically 1, which is not 0. So this also diverges by the nth term test. And for this last one, limit as n approaches infinity of just ln of n. Well, ln is a very slow growing function, but it does grow forever if you plug infinity into it. So this goes to infinity, which is not 0. So this also diverges by the nth term test. So the only one that we couldn't use nth term test to prove divergence on was choice B.